Okay, should be okay, good. So thanks very much. Steve was kind. I actually graduated with my PhD in 1994, so slightly more than a few years ago. But no, I really enjoyed my time at Stanford, so I'm always happy to help out and continue on with it. So I'm going to talk to you today about the future of computing, or at least IBM's vision of it. And I'll first of all note that is Yorktown Heights, New York, our headquarters for research. As was mentioned, I actually run the San Jose Research Lab in Almaden, which is just south of here in South San Jose. But it's all part of a network of actually 13 or 12 labs right now globally. So we have 3,000 researchers. I think we're pretty much the only company left that has an actual research division that's completely separate from our development labs. So this group was started back in the 1950s, really with the idea of doing much more academic style research that would then feed into our development labs or start new businesses or, or do great science. Very much along the Bell Labs model. We've managed to survive. Obviously, things have changed a lot in the industry since those days when there were lots of labs out there. So I mentioned Yorktown Heights is the headquarters. I run the Almaden lab. Zurich is the other lab that was started about the same time. Those are the three sort of big labs. The other labs you see largely were started in the last 15 or so years, 10 to 15 years. They tend to be smaller, and they tend to focus much more on computing or computation that would be applicable to the local area. So if you think about like in Africa, we have 2 sites right now. And I'm pretty sure we're the only company that has actual research labs in Africa. But the point is, if you're going to do technology for a place like Africa, whether it's banking or healthcare, you really need to understand the infrastructure or lack of infrastructure in many cases there versus here. So the kind of solutions you're going to come up with are going to be different. So we thought it was valuable to actually have researchers even involved there very early on. The research, our goal is to be famous for science and also vital to IBM. So we have definitely been contributing to a lot of the breakthroughs you probably think about in computing today. The DRAM was invented by IBM. The disk drive was invented by IBM. In fact, there's one right down in the front of Almaden, because that's where it actually was invented down there. Relational databases, lots of other things. Fortran as well, whether you like it or not, came from IBM. So we pride ourselves on that. That's making the vital part. But we actually do also pride ourselves on the science. So our researchers are actually rated on, are they going to conferences? Are they leading conferences? Are they doing keynotes? Are they publishing in the right journals? Are they parts of writing textbooks and things? So it's kind of a halfway between being a professor and being like in industry and development kind of side. We actually are still fully integrated. We literally do a lot of work actually at the materials and device level, which we'll talk a little bit on, and kind of goes into the future of computing. I think we're, again, the only people who are still integrated from literally that machine. Which one? That one there in the upper right is in the basement of Almaden, and literally they move individual atoms around in it to try and create new materials, versus going all the way up to giant systems, exascale systems, HPC systems, obviously, as well as a lot of AI and algorithm work. And so we actually have a diversity of disciplines there now. People who have PhDs, of course, in electrical engineering and computer science, a lot of those around, but biologists, genomicists, people who specialize in finance, marketing, mobile devices, robotics. So the mix is really because of the fact that as we see computing going forward, it's less just about making a giant server that's going to do your data automation processing in the back office, and more about how you can apply things like AI or quantum computing to solutions that really are part of your actual business and part of your actual industry. So we need to have researchers who actually understand some of those industries and how we can apply computing to them. So with that background, I'll actually start into the real thesis of the talk, which is, what do we see as the future of computing? And the sort of conceit I'm going to put around it to discuss it is, we really see it as a combination now of bits plus neurons plus qubits. And we'll talk about each of these as we go forward. So we'll start with bits. And really for each of these, if you think about it, we've always been about trying to figure out how you can manipulate information. That's a lot of what computing has been about. And the very first insight was, arguably like Claude Shannon, Turing, people like that, who realized that if you take mathematics and you combine it with information, you can actually do some amazing things in terms of manipulating it and coming up with really interesting capabilities far beyond just doing math equations, right? So that's what really is the basis of today's computers, everything from your phone up through the supercomputers. And it was based, of course, on a bit, right? So the idea that you can represent information as a bit, just a 0 and a 1. This is the very famous Gordon Moore's law chart. 1965. He was the first one who noticed that, this kind of interesting sort of insight was great in theory, but it looks like we actually are now doubling the number of transistors we're putting on our systems every year. And if that continues, that means we can process more and more bits. And if that continues like that, we can really do some amazing things. And I think, of course, he was right. I mean, and the reality is, even though Moore's law is clearly, we'll be polite and say slowing down, at this point, at the same time, it's had a run for almost 50 years, right? Which is a pretty amazing thing. And the fact he predicted it with just 4 data points and was right on a semi-log plot for 50 years is pretty impressive as well. So that really has driven what we know of for most of computing today, or at least up till now. But there clearly have been things that have been changing just in really about the last, say, 10 years or so, as Moore's law has started to slow down, but also as different types of workloads and different types of problems have come up that really our current architectures don't necessarily solve very efficiently or at all, depending on the level of problem we're talking about. So I think one of the big focus areas right now in the industry is how do we solve some of those problems? And the first set of those problems really comes under the whole rubric of AI, or artificial intelligence. And I think some of the insight here was, clearly our brain does certain things really, really well, right? I mean, it's really bad at matrix multiplication or high precision floating point, but it's really good at recognizing a person in a crowd out of nowhere and recognizing that face, or a crowded conversation, picking up on the one voice it's trying to hear and actually understanding what it's saying, right? Those are things that we kind of say are AI if the computer does it, and of course it's very difficult for computers in most cases to do it well. It's only been recently that they've gotten any good at it. So as we go forward, we think more about how can we learn from biology, because obviously the architecture in our brain somehow has done something differently, and how do we combine that to manipulate information in the future. And I think that the key structure that has been causing a lot of the interest in the past, say, 8-9 years, has been the neural net technology, or deep learning, or whatever you've heard of it in the past as. It actually was born in the 1940s, as when the first group started to think about, hey, could we try and build something that looks a little bit like the structure of the brain? At that point, it was understood, at least, that it seemed like there were neurons in the brain. They communicate by spiking to each other, and somehow this collective effect causes a lot of what we think of as thought. Could we do something similar as well in a neural net? So the simple idea of a neural net is you create these very simple nodes, and it can be in software or hardware, of course, usually in software, and you just show the neural net something on one end. You put input bits on one side. It does a very simple manipulation on it and sends it to the next layer, and that continues on in the end. And if the weights and the calculations all the way through are correct, this neural net can identify what comes in at the front end. And I'll go through a little bit more detail on what that might mean. But I think that the important thing to point out here is this really is something that is, in a sense, self-trained or self-learned. You don't actually program it the way you think about programming other things. And it emerged largely because of the failures of what we've been trying to do in the past for artificial intelligence, which was write up rules for this. So if I want to identify a cat, I could say a cat's about this big, it's got fur, it's got a tail, it's got pointy ears. Sometimes it doesn't have a tail, sometimes it doesn't have fur, but you'll get those exceptions. So you can see how it becomes really impossible to write enough rules for the computer to really recognize effectively images or anything that's not in a structured format. But the brain, of course, does it quite well. So this is why this really came in. And as I said, the implementation really is very straightforward. And just in case people are not familiar with how it works, you basically just put a number into each of these neuron nodes. It does some sort of nonlinear function on it. The sigmoid is fine, but it has to be nonlinear. That's clear. And then it sends its output to the next neuron in the columnar structure according to some weight. So in some cases, it's going to be very strongly connected, so that weight will be very large. Some cases will be very weakly connected, even a 0. It might have no connection as well. And the next neuron just takes in all the inputs and adds them all up and does the function again and passes it on through. And so by doing that, is able to train itself to do some pretty interesting things. So the first thing you have to do with a neural net is train it. And you literally usually start with some structure between the way how the neurons are connected. This just shows a fully connected network. There are different versions, but something like this. And you just start showing it pictures. In this case, we're using pictures of handwritten digits to show it to it. And you've decided that it's going to show digits 1 through 4. You want, of course, the correct digit on the right-hand side to light up, depending on what it is. So in the training phase, if you show it that, and you pass that through, and that one there lights up, well, that is a 2, so that's incorrect. So then you go back and you look at all of the various neurons that had fired, that made that thing fire there, and you decrease their weights along the way. Just say, no, you were wrong, so therefore you're going to get lower weights. So next time you get that same set of bits, you're going to send less signal out at that point. And you do this back and forth, and you do it again and again until eventually you get to the point where it's fully trained. The weights themselves have somehow self-adjusted, and again, this is actually in some sense a black box process. So then when you show it a 4 in the future and you're in that phase, you see, oh, a 4 does light up now. And by the way, even during the training phase, if it lights up correctly, you'll do the back prop and reinforce all those weights, right? You'll increase them, say, yep, you guys all got it right. I'm going to make those higher and higher. And this is the way that we actually train neural nets today. And in the end, that can turn out to have very good results. Much better, in fact, than maybe we would have expected. And in fact, if you talk to the math theorists who try and study this stuff, it's honestly not entirely clear why neural nets work as well as they do. If you just go through the sort of parameters and numbers you're dealing with, it's not clear that they should do it as well as they do. It's also not clear, what rules they're learning in those patterns to give you the answers on the other side. And that's a real limitation for AI going forward, which we'll talk a little bit about later on. But, so how good can these things get? Well, as I said, neural nets were known back in the 1940s. There was a lot of research going on in them in the 1970s and 80s, and they were just abysmal failures. I mean, just, the rules were better than using neural nets. It was such a failure that people talk about the AI winter, you may have heard of, in the 90s or so. AI became such a failure in many people's eyes that it was almost embarrassing to say you worked on AI. So, good researchers stopped working on it or stopped talking about working on it and kind of went underground because it just clearly wasn't working. But then something very interesting happened about 2010 or so. So all along there had been this undercurrent of people continuing to try to work with neural nets and play with them. And their error rates were always in like the 30, 40, 50% range, nothing that would be at all useful. And then somewhere around 2010, 2011, in one of the big contests they used for identifying images, the error rates started to plummet, and they got lower and lower. And you can see within the space of 5 years, they went from almost 30% to in 2015, they were actually better than human level. So today, a well-trained neural net can actually identify images better than humans on average in terms of the error rates. Same with language or listening, get audio information. Doesn't mean it understands it, by the way. That's a whole different question. But at least it can actually identify and say what the words are or what the image is. So why'd that happen? So I think those of us who are engineers would like to say we got really good at the algorithms. That's actually not the case. In most cases, the algorithms and the structures we use are the same ones that were used back in the 70s and 80s. To be fair, we actually are now improving them a lot now that we actually have them working and running. That you see a lot of work in the literature right now that actually is improving the algorithms, and we're getting more intelligent about it. But that wasn't the initial breakthrough. The initial stuff was really the two things on the bottom. One is we finally had enough data available to actually train the neural nets. So that process I was talking about of changing the weights, as you can guess, it's kind of a random stochastic process. It takes a lot of labeled images to actually train that. So the joke as to why neural nets are so good at identifying cats on the internet is because there are a lot of cats on the internet. So you can actually get enough training data to actually go do that. But the other thing is compute. You have to have enough compute power to run these very large neural nets. You have to have a very large, deep neural net with lots of weights and numbers going on to actually be able to identify something complex and also to run all of those training cycles we're talking about to actually get them trained up. And CPU architecture, even as it's gotten better and better, really was not up to the task. I mean, you could do it on CPUs. Small ones you can certainly do, but large ones you could do. But what really made the difference is when GPUs came into the picture. And it was a researcher who had this sort of insight that the GPU, the graphics processing unit that we use for accelerating graphics in general, was really good at running the same kind of math you needed to go to run the neural nets, and was able to run it, of course, highly parallel processes, great for throughput. It's obviously set up for real-time, complex graphics. So in a sense, it was literally just dumb luck that this happened to work. But someone figured out it was going to work, and they started to apply it. And of course, now everyone uses GPUs. For doing any kind of training on neural nets. And it made all the difference in terms of our ability to get to these levels at this point. So I think the good news is at this point, specialized AI works, and it actually works incredibly well, right? You can do language translation, speech transcription, language processing, visual recognition. But these all are really sort of I'd say point tasks, right? These are things that we can do that are point tasks. We need to kind of take the next step forward. Nonetheless, it's driven a ton of interest among you in the audience, students in general. These are just some quotes on the attendance or the enrollment in Intro to Machine Learning in MIT. It's went from 300 in 2016 to 984 in 2019. You can see the numbers there from Andrew here at Stanford as well. I mean, clearly, in many ways, AI has become the new IT in terms of what people think about really focusing on. Which then means also from the hardware side, which we'll spend more time talking about, we need to keep thinking about what we do to make sure we continue to run this. The software guys might have the fun of getting the app out, but it runs on something. Even in the cloud, there's hardware up there, so we do have to run it on something. So where are we right now in AI? So I think, as I said, we kind of are getting out of the narrow AI range, where we've proven it can do something very useful on individual tasks, and in fact, better than people can do it. So that's just the first clue that maybe this can do same thing IT has done in the past, start to automate processes at a scale that humans can't do, which then hopefully allows humans to continue to do higher level processes over time. But we're now moving into what we would call the broad AI phase, where we need to take these sort of like, say, interesting parlor tricks and say, how do I actually use these for something? What's something I can do with it that will help me in my business or enterprise? Obviously, IBM thinks a lot about that sort of applications in particular. And so that's really where we are now. And that means a lot of things that I'll talk about in terms of things we have to change with AI. Beyond that, at some point, and we're putting it about 2050 or beyond, we may reach a level where we could talk about general AI, where you'd actually see something that actually looks intelligent from what a human would say. So this is like, the scary robots, Terminator, Skynet kind of thing. I know a lot of people talk about it being concerning today. I'll tell you, I wish my AI were even close to that good, but there's no way we're going to hit there anytime in the really near future. Doesn't mean we shouldn't be worrying about it and paying attention to it, but I think we've got a long way of really exploiting AI right now to really think about how we use it well before we get to a point where we have anything that really has the autonomy to actually be able to make decisions on its own and do things that we would consider intelligent. So these are kind of the three areas I talked about. So narrow AI we've already defined basically as deep learning, being able to do things at a very high level. Broad AI, where we are today, we want to get to the level of doing some learning and reasoning. And be able, which will help us not only have the system be more useful, but also hopefully more explainable, so it can explain why it's made the choices it's made, or more importantly, when it makes a mistake, that we can understand why it made that mistake. Why does it think this dog's a cat? It's looking through a bunch of numbers in a neural net. It's pretty hard to make that decision or figure it out. And also, we need to be able to learn with much less data. Because of the fact of the one in the middle, we need to move multitask, multi-domain. There are a lot of cats in the internet, so we can train it for that. But if I want to train it to help a radiologist doing X-ray images, in a sense, there are lots of X-ray images out there, but actually getting them all together, labeling them up, and actually getting training on them is incredibly difficult. So you'd much rather be able to learn on a much smaller subset. Similar to other enterprise areas, there's just not that much data when you look at for millions of examples of something that you could actually put into a system and train it. So you have to get much better about using small amounts of data and training it, and then being able to extrapolate once you have a well-trained network to move it to the next domain over. And we find today if we train a natural language processing system, say to do read contracts, like for a business to help it understand the content of the contracts, we might train it really well on a whole set of contracts from a company. We might go to another company that is using exactly in the same business and it fails on their contracts because the wording is slightly different. Now a human who was an expert could read both of them and be completely fine, but the system you almost have to start from scratch training it again. Because again, it's not necessarily learning the way we learn or reasoning about what it's seeing the way we think about this. And in fact, if you think about even the way humans learn, when you were a little kid at some point, you were going down with your mom someplace and you pointed at something going down the street and you said, what's that? And your mom said, well, that's a car. And so you just got one labeled example of a car. Now your brain's going to see really thousands and maybe millions of different examples of cars after that, none of which will be labeled. But your brain was able to take that one labeled example and extrapolate and say, oh, car, 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 car. And it's amazing how quickly kids can do that, right? And even more amazing is at some point, you probably saw something on the road and you said, that's not maybe a car, I can't tell. So you thought to ask your mom, what's that? And your mom said, oh, that's a truck, right? So now, okay, trucks, they're bigger, I see. They're like this, then truck, 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 car, car. So the thing is, with just very few labeled examples, your brain is able to then take that and apply it to all sorts of other examples and extrapolate and come up with this classification is still good. And even more interestingly, it seems to understand usually when it can't extrapolate that far and knows enough to go and say, oh, I got to go figure this one out. It might be a car, but it seems slightly different to me. we're nowhere close to that with AI today, right? It doesn't have any way of understanding even what it's seeing, much less knowing how to classify it. But it's something we work on a lot. All right, so back to where we actually run this stuff. So today, both training of the neural net as well as inferencing is run primarily in the cloud on data centers. Over time, we would like to see that move out towards the edge, particularly for inferencing, when you're actually just running the neural net. Certainly applications like your cell phone, where you'd like to have, you're talking to Siri, you ask her a question, you wait for that delay, because it usually goes up to the cloud to do most of the language processing before it comes back and gives you the wrong answer anyway. But without the delay, at least it would be less annoying. Or something like a car, obviously a self-driving car, it has to make a decision about a pedestrian walking in front of it, a couple hundred milliseconds before there's a problem. The cloud figures it out 10 seconds later, doesn't matter, at least not the pedestrian. So these things require us to do it at the edge, which means we have to think about, even with what we got today, we aren't nearly at the point where we can actually do that. In terms of where they actually run, they run in the data centers, but they run on different types of architectures. So on the side here, you see kind of largely CPUs, advanced analytics, NoSQL, Hadoop analytics. So really think about that as all what we used to call big data, right? Big data analytics was the big buzzword, say 10 years ago, and it was all about getting benefit out of the data, largely in databases, largely structured, but really for businesses to be able to do that. That continues to be really the mainstay, by the way, of what we do with information processing in the industry, and it runs still on very large CPU systems. Once we get into the AI side, where you're having systems that are learning or finding patterns or training themselves, some of the ones that are more rule-based can still run on CPUs, and we still do that. As you move into machine learning or even deep learning, more and more they run on GPUs, but also on FPGAs. FPGAs are also quite good for parallel processing, particularly if you have a specific architecture you're looking for. And you're already starting to see the race to ASICs. You're seeing companies come out with specific chips now that are designed for running neural nets in particular. So the TPU from Google is an example of that. And that's because we realized that the GPU, it was designed, again, for graphics. It got lucky and has a really good market right now in AI, but that also tells you probably there's better architectures, or at least improved architectures one could think of to run it. And why do we really need to get down there? If GPUs are doing a good job, why do we really care? So that's a picture of ImageNet, or at least a subset of it. And ImageNet is sort of the premier set of images out on the internet. Fei-Fei Li, by the way, at Stanford, was the one who really championed this early on. And that's how you train your neural net to prove it's really good. So if you want to fully train on the ImageNet database out there, if you had 4 GPUs, it would take you about 16 days and 385 kilowatt hours to train that. Now, obviously, you can add more GPUs. So if you had 256 GPUs, you could do it in about 7 hours, which is more reasonable. 450 kilowatt hours, you spend a little more energy on it. But either way you look at it, that one model training is 2 weeks of home energy consumption you just use to do this training. And of course, if you need to retrain it, or you need to add a new cat to the database, you got to go do this again. So clearly, it's okay if you're using it for large applications in an enterprise. You're going to do some training and then go do a bunch of inferencing. It clearly says we have a long way to go, though, if we want to make this efficient, to actually be able to do lots of training in lots of areas on lots of different topics. So we kind of see a roadmap right now on where we're going with hardware for this. Right now, and in sort of the near future, we obviously will continue to exploit GPUs, and we'll also look at other ways we can use digital technologies, so normal digital CMOS technologies and chips to get even more performance with different architectures, and even things called approximate systems, which I'll talk about. Beyond that, we actually are also working on thinking about, are there different devices we should put on the silicon chip that would do this more efficiently? Now, obviously, the digital CMOS transistor has been really good for digital, which needs high precision, high speed, lots of attributes that work really well for HPC. We know our brain is nowhere close to that. It's slow, it's got very messy connections, so maybe you don't actually need all of that. Particularly if you think you can go to approximate or low precision systems. Are there analog devices or devices that look like analog devices that could in fact do it more efficiently, and could we use those instead? And then lastly, there's also a role for quantum computing, which I'll talk about in the last probably third of my talk, both for AI but also just in general what we're doing with quantum computing. So for today, of course, what we're going to do is we're going to use GPUs. Right? That's what's going to happen over the next few years. So this is just an example of the Power 9 server from IBM that came out probably about a year and a half ago now. And it was the first one that we really labeled as an AI-enabled system, because for every power CPU, we had 2 V100s from NVIDIA, our partner for the GPUs. And it was designed with these extremely high-speed NVIDIA links, 150 gigabytes per second between the GPU and CPU. And you can guess why. If you're moving a ton of data around back and forth to do this training, all of those connections make a huge difference if you really want to be able to scale to high performance. So finding ways to design at the system level, even with the existing devices, makes a huge difference in the actual performance you get. And in fact, if you looked at this, we did a challenge to see how well we could distribute it. We were able to actually get 95% scaling efficiency with this 256 GPUs, and actually got a 4% increase in the actual accuracy and performance we were getting out of it. But that comes because you designed a system to actually think about how you're going to process this data, which is different than the way you might design a system if you were just thinking about normal sort of floating bit precision and that kind of, those sorts of workloads along the way. And in fact, it's even changed the supercomputing roadmap quite dramatically in a quite short period of time. And not just from the renaming that Steve had to do from HPC to HPC AI, but even in what we see in supercomputing today. So this is just some shots of supercomputers throughout the years from my favorite anonymous company. You can probably guess which one it is. Throughout the time. At the same time, we've also been working on advances in AI, and those two things I will say have been almost completely separate. Even the AI workloads we were running in the past rarely ran on HPC systems, probably ran on big servers and things. Checkers, then chess, then the Jeopardy game, and most recently we did a debater architecture. But in 2018, when the Summit supercomputer came out at Oak Ridge National Lab, which was IBM and NVIDIA, Mellanox, and others who were part of that, it was became the world's first fastest supercomputer. So we got the honor back from the Chinese that had it up until that, so we're excited about it. But if you looked at it, it was very interesting because obviously it could do the 200 petaflops. That was the big headline number. Had over 9,000 Power 9 processors, but had over 27,000 GPUs built into it. And that was very much at the request of the funding agency, the DOE, because they had realized that their supercomputers right now have got to be able to run not only large floating point, which is still going to be very important, but large AI workloads as well. And that's something that's changed literally in one generation of supercomputing. It's now table stakes. You must be able to run these just as well as you run everything else. And of course, it takes 15 megawatts of energy consumption, pointing out that the power is still an issue even at the supercomputing range. That's a lot of power. I mean, obviously, you can build a facility to run it, but that's a lot of power to consume for a system. So how do we think we can improve on this trend line? So right now we're using GPUs, and this is kind of a plot of performance per year. Again, a semi-log plot because you have to do that in the chip world always. So GPUs, just empirically, we've noticed have been going at about 2.5x performance per year. The trend has been. There's already some signs, even from what's been come out or announced for like 2020 and such, that it may be starting to bend over. It's hard to say for sure. It could still be on a straight course, but it looks like it's starting to bend over there. And it's not surprising because GPUs are under the same constraints that every other chip is, which is they get most of their performance by continuing to scale, and Moore's law scaling is becoming less and less feasible, or at least less and less efficient in terms of what you get out of doing it. So it's not surprising they're starting to pass over. So of course what we'd like to do is keep it on that line, so we have a nice straight semi-log line still we can look at. So how can we do that? Well, the first thing we've done a lot of work on is analyzing the types of workloads that run. Because if you're going to bother to try and build ASIC kinds of things, you better have a big workload that's worth doing it, right? The only reason we wrote floating point engines is because there's a huge workload available for floating point. Well, if you look at all the various types of neural nets and things that are running today, one thing they have in common is a huge amount of that red. The gem is the benchmark that's looked at there, but basically matrix multiplications. There's a lot involved regardless of what you're doing exactly. And there's other things, of course, that are also important, but that at least is one. If you could accelerate that part, it would make a big difference for a lot of the neural nets that we run. And that's, of course, what GPUs accelerate fairly well today. So if you're going to do it, though, you got to really think about all sorts of things about how you're going to actually make this work well in a system. So we look at algorithms application level. Are there ways we can compress or quantize some of the work we're doing so we're moving less data around when we're trying to actually do the training? Are there ways that we can actually not move data in and out quite so much? GPUs, when they do training, they actually move in every layer of the model every single time they do and do a batch of images at a time. It's a huge amount of movement back and forth that arguably it would not be necessary if you built the architecture such that it could hold all of that model information in the chip at once. And then along with that is what is the right way to flow the data through so that you actually get a true data flow architecture rather than this back and forth, back and forth. So if we do all of that, then we can also think about, well, how do we actually change the chip itself to try to be more efficient? And as I said, the first thing we're thinking about is using AI with approximate cores. And so this really means going to lower precision, which I realize to an HPC audience sounds like complete blasphemy, but bear with me. So if you think about it, this image here is a very low precision image, but I'm guessing that no one had trouble recognizing who this woman is, right? And that really is the key with AI. In the end, I don't care if through the foggy window I can't quite make out the features of the person's face walking up the step. I mean, if it's, as soon as I say, oh, it's my mom, I have the answer. I don't need to know everything else about what her face looks like at that moment. And that's really the same idea here. We don't actually care if all the matrix multiplies are exactly accurate. What we care about in the end is, every time I show it this picture, does it get the right answer on this side? So there's been a lot of work looking at how you could actually reduce the precision of those calculations and yet still get the right answer on the other side, right? There's a limit, of course, to what you can do there. But there's a lot of push for doing it, because every time you reduce precision by a factor of 2, you actually gain a factor of 4 in power and area. So there's a huge gain on the chip level if you can do it. So there's been a lot of work at looking at different versions of it. We had a paper in IEDM and at NeurIPS this year, both showing how you could we'd already gotten to 16-bit, we moved down to 8-bit for training. And you can see that we actually are matching on the right-hand side, or left-hand side there, you can see we're matching pretty well to the full 32-bit floating point baseline for the training on the ImageNet there. This other plot is just showing some stuff under the covers. It's not enough just to reduce the precision. I mean, that would be a fairly easy thing to do, but you have to really think about where you're reducing the precision and what implications that's going to have. So if you think about the method of doing the neural nets, you've got multiplications, you've got additions. Well, when you do additions, if you have a really big number and a really small number and you're in low precision, we all know what happens to the small number. It just disappears. So we do chunking, so we're actually we're adding things up at number levels that make sense for the precision, and then only later actually combine up the ones that have larger differences. And we also do things like using 8-bit for the weight activation, error, and weight gradient numbers, but sticking with 16-bit for the update and accumulation. So there's a lot of subtlety to actually reducing the precision, but yet you can, as I said, you gain a huge amount in terms of area and performance when you do this. Beyond that, we think about, if we're going to go to low precision, then we could think about analog devices instead. And if you recall, or maybe you don't recall, but in the 1950s and such, computing was mostly analog. Analog computers were the way you did things because we didn't really have digital technology. Vacuum tubes were coming up, but even they were fairly inefficient. And analog actually is really efficient for many types of calculations, including multiplications and additions, as I'll point out in the next page. But it's also incredibly error prone, right? And it doesn't scale well at all, and it has very low precision from what we would describe today, which is why we rightfully moved to digital when we went forward. But maybe for this particular workload, it would make some sense. And if you think about it, your brain is clearly not digital at all. And that most of the estimates that I've seen say that the neurons probably are on the order of maybe 4 bits of accuracy if you were going to try to somehow make that quantification. You might argue some of your colleagues are a little lower than 4 bits, but something on the order of 4 bits along the way. So clearly the brain does it with lower precision. So why would this make a difference? Well, obviously part of it could be the efficiency of the multiplication, but if we could also figure out ways to get around this problem we see in digital architectures where we have a whole bunch of data in the memory and we have the compute over here and we're moving things back and forth, again, clearly not the way the brain works. Are there things we could do by going analog devices and thinking more about that? And the idea would be, if you think about that cross point of neural nets right now, which if we actually put it in hardware, mostly it's simulated in software, but if you put it in hardware, you could actually make exactly that structure. And you could actually make a cross point where every neuron on, say this is the first column on the vertical and it's the second column on the horizontal. And of course all of them then run together so that all the inputs from one go down to outputs of one go down to the inputs of the next. So if you actually made cross points there and you put there some material that actually had a variable resistance, and you think about just running a current through it. So if I take a resistor and I run a current through it, well, V equals IR, so that's basically a multiplication. And if I take all those currents in one column and take it down to the next node, well, by Kirchhoff's law, all the currents have to add up. So I've literally just done my multiplication and accumulation by just running currents through a resistor, right? So the key is you have to have something there in that unit cell that is a variable resistor, right? That becomes the weight of the connection between the two. And by the way, of course, if that's the variable resistor, that is the model data, right? You don't need to move that in and out. You've got it set there in that actual connection. So you get around that bottleneck problem. Now, it turns out there are already materials like this, phase change materials, PCM you may have heard, which are being used, and there are at least a few commercial products, although it's still fairly slow in the industry, coming out that use materials that actually you change the crystallization state, which is what that little animation is supposed to show, that changes then the resistance of that device. Now, they were designed to use as memories, because you get multi-state memories there, right? Multi-bit memories for storing things. We would like to just repurpose them, at least initially, for actually those kind of variable resistors between the various connections. And we've already done some examples of this. There was a paper at IEDM where we actually showed for the first time, we did 2 of the layers of the neural nets using this. The rest of it was done by sort of standard digital processing. But we showed you could get the exact same accuracy at the end, even though you had 2 of these that were actually running like this. And the projection for how much power we were saving on those 2 layers compared to if we'd done it digitally was about 200x. So it's a gigantic savings in power that you gain if you're able to do it this way. And the last step is, as I mentioned, we're using some analog materials today that were already out there for memory devices. Again, clearly not optimized for what we would actually like to do. So can we think about actually optimizing those materials? So if you look on the left-hand side there, that's what a material looks like right now, a phase change material in terms of the conductivity as a function of how many voltage pulses I put on it to crystallize it. So you can see as I'm going up in resistance, the red dot's going up. It goes up to, the blue dot's going up. You can go very nice linear steps. When I try to go the other direction to reduce it, boom, it resets. Which is fine for memory. You basically, it's just like flash memory, right? You can set it to some value, then you have to erase it all the way back down to 0. But this thing, that's not what you want for this. You want to be able to adjust the resistances up and down during the training period, right, till you zero on the right point. So you want something that looks more like those red dots instead. So we have looked at other things besides phase change materials. This is electrochemical random access memory. So basically it's a transistor that's got some free ions in the gate layer, and you can move those back and forth, which changes the threshold voltage of the transistor. So you can see you get a nice sort of linear looking structure there on the right hand to the left hand side of it, which may in fact be better for what we're trying to do. At the same time, we also are looking at can we find algorithmic ways of doing it. So if you have something that's not symmetrical today, the black line is what you'd like it to look like. The blue line is what it actually looks like when you try and actually program it, because you can't actually zero in the weights correctly if it doesn't have the right symmetry. On the other hand, if you actually know what that shape looks like fairly well, you can do some algorithmic work that would actually correct for that. So you actually can find, you can get them to line up together. Of course, the problem is that actually adds some overhead to what you're doing now on the software and the algorithm side. So finding the right balance between having it be close enough to symmetric that you don't have to do too much over here, but since you'll never get it perfectly symmetric, using some of these techniques to actually compensate would actually be helpful. So finishing this section up, basically we look ahead and we see now a plan to go all the way down to various lower levels of precision, even down on the inferencing side to maybe as low as 2 bits for inferencing. I didn't talk much about it, but obviously just I think conceptually you can think about training is where you really need to have a little bit more accuracy, because you're going to try and shift weights up and down by small amounts until you get the right levels. Once you're just going to run inferencing, you can probably run it with less accuracy and still get something that actually comes out with the correct answer. So we're doing a lot of this research work at our Albany Research Center, as well as the labs you see here. I bring this up because we just announced a big partnership about 6 months ago with the state of New York, but also with Applied Materials, Lam Research, TEL, many of the big semiconductor companies really focusing now on how we can actually make the chip level at least move forward along the way. All right, so then the last third of my talk here, I want to talk about what else could we do. So we talked about how using biology and information may help us change the ability to run AI systems and AI types of workloads. But there are other sets of problems which are not normal computation and are not AI that we also can't solve on classical systems. And for those, maybe there's something else we can learn from the science side of it. In this case, looking at physics more deeply and seeing, could we use quantum mechanics or some sort of quantum effects to actually be able to solve problems we couldn't solve any other way. And this one is actually a little bit more recent. So in 1981, IBM and MIT hosted a big conference at MIT with a bunch of the world famous physicists at the time to talk about quantum information theory. Just talk about, could you use quantum for something? They talked about transmission and encoding, all sorts of things. Now, for those of you who aren't physics groupies, I'll show you that guy there is actually Richard Feynman, and he was one of the guys that was at this conference. And he was the one who arguably deserves the right to be said that he came up with this idea of quantum computing. And what he was talking about was he said, we're doing a lot with computation right now, but I'm not so happy because nature isn't classical. And so if you want to actually simulate it, you better have a quantum system. He said it a little bit more colorfully along the way, but he really came up with this idea there are certain problems, and he was looking at chemistry in particular, which are fundamentally have huge numbers of states involved with them, so the problem blows up very rapidly when you're trying to solve it on a classical system. So that really started this whole idea of what could we do to actually do this, do something else. And what they immediately zeroed in on was taking advantage of quantum mechanics even down to the level of how you represent information. So obviously the bit, we all know, 0 and 1, we talked about that earlier. The quantum bit, or the qubit, which is the equivalent, can also be in a 0 or 1 state. But because it's a quantum element, is some sort of quantum system, it can be in a superposition of those two states. So in other words, it can have a probability of being a 1 or a 0 at the same time. And it's a well-defined probability. Well-defined if you go through the math, and you can say it's got an 80% chance of being a 1 or a 20% chance of being a 0. And you can manipulate that in a quantum system to actually set it to different levels of probability that it's going to be a 1 or a 0. So in a sense, you can actually represent multiple states at once. So that's one of the things where you can get more power out of, or potentially more performance out of a quantum system. The other important thing about quantum mechanics, though, is that you can entangle qubits. So if you have a qubit that's in some sort of probability state between a 1 and a 0, in a superposition state, say, and you have another one, you can entangle them such that when you do something to the bit number 1, instantaneously that determines what's happening with qubit number 2, or 3, or 4, or thousands on. So if you think about it, this, I'm going to be really clear for the physicists in the audience, this is not actually how it works, but it's the best way, I think, to visualize it. If you had 1,000 qubits and you entangled them all, and you did an operation on one of them, you simultaneously do that operation on all 1,000 of them at once. For, no energy, no even communication. That's one of the things Einstein hated about quantum mechanics, is it's literally spooky action at a distance. That 1,000th qubit could be on the other side of the world. It still instantly knows what you did to this qubit here. So this entanglement's a very powerful concept. So I think if you just think with your sort of computation hat on, you've just got a massive, massive parallelization in what you're doing with your computation, if you can map the problem onto it, and we'll talk about that. So in the past, we have Moore's law. As we doubled the number of transistors, we roughly doubled the number of bits we could work with. That's obviously not exact, but it's on the order n. You go up by the order n as you go forward. With qubits, it's actually 2 to the n. So every time I add just a single qubit, I double the performance capability. So just to use numbers, if I had 5 qubits, 2 to the 5th is 32 states that I could somehow represent there. If I had 10 qubits, so I doubled them, I now have 2 to the 10 are 1,024 states. So by doubling the number of qubits, I went from 32 to 1,024 states. So you can already see how rapidly exponentials beat a linear approach here. And that's why people are excited about using quantum systems. This is a pretty marketing picture of our quantum computer. It actually is quite a pretty computer. It's actually probably one of the nicest looking computers I've seen in a long time. But really the idea is you have to still put in classical qubits, or classical bits on one side. You then manipulate the qubits in the state that they're going to be in the bottom until you get to the right answer. When you read them out, in quantum mechanics, you will always get a 1 or a 0. You don't get some weird intermediate number. So when you go to read them, you will always read one or the other. So this is the way the system actually looks in real life, or at least the one in our lab right now. The system without its cover is these sort of layers of copper or gold-plated cooling devices. This is a dilution refrigerator, basically. You can see the temperatures of these. You need to get down to very low temperature. The chip is going to be at the very bottom where Jay's hand is there. And that point is 0.015 or 15 millikelvin, so 15 thousandths of a degree above absolute zero. For reference, space is about 2 to 3 Kelvin, so that's like 200x colder than space. You really are isolating this to very, very cold temperatures. You also have a bunch of electrical insulation around it as well. And that's all really, partially because it's because they're superconducting, but you could probably do that like 4 Kelvin or so with this particular set of materials. It's mostly to isolate it, to keep these qubits in this very fragile superposition and entangled state. And that really is the biggest challenge right now with quantum computing, is how long can we keep those qubits in this state. In terms of the way we actually operate it, we actually have a rack of analog electronics. There's nothing digital about this system. You basically are manipulating these qubits, and I'll picture on the next page to show what they look like a little bit more, with 5 gigahertz signals. Microwave signals come in to move them into different states and rotate them around and entangle them. So it's all very analog. Actually, that reminds me always of the ENIAC. You ever see the picture of ENIAC when they programmed it by putting all these different cables into different systems? Very much at that level right now when we actually program these things. So looking down there, the actual qubit is a superconducting Josephson junction, so a transmon it's called. It's basically a harmonic oscillator, so it oscillates back and forth. It's a nonlinear oscillator. That's the reason it needs to be a Josephson junction, which means that the energy levels between the states of 0, 1, and anything above it vary in height. So that guarantees you actually stay in the 0, 1 state and don't suddenly jump up to some state above that. And it's basically, though, a way we had to program it is we just put in signals that like maybe bump it up to the next harmonic or take it down to the 0 harmonic. And we can entangle them so they both are in some state between those two. So if we do all this work, what can we do in terms of computation? So I mentioned chemistry was the original sort of impetus, at least for Richard Feynman. And here's an example of it. So caffeine, a very important molecule to get through college, as well as life. It's a fairly small molecule. It only has 95 electrons. But it turns out if you actually wanted to do an HPC simulation of this in a classical system, and you wanted to do it exactly, which no one does, it would take 10 to the 48 classical bits to actually represent all the potential states there to actually zero in on what is the actual ground state of this device. And that's a very long number. You see 48 zeros. And again, for reference, the planet Earth, about 10 to the 50 atoms. So literally 1% of the atoms on the planet Earth would somehow have to represent classical bits in this giant system you just built to be able to actually simulate this molecule. So when we say there are some problems you can't solve with classical systems, we seriously mean it. You would never possibly be able to build a system that was that large. So of course what we do is we do lots of approximations. So people do a lot of HPC simulations on chemicals, but they do it on fairly small subsets of models. They do make a lot of approximations on how interactions are going to happen, on what the orbitals are going to be doing. They do only the valence electrons. They don't try and do the core electrons. You know, all these things we do today to enable us to actually make progress, but it would be great if you could actually do this exactly. And a quantum system would be 160 qubits. So that's a very approachable number, right? That's something that today our prototype systems run with about 50 qubits. Now they aren't high enough fidelity or low enough error rate to actually be able to do this yet, but they already are getting close. So as we see the roadmap going forward, sort of the equivalent for Moore's law is going to be to increase the quantum volume on these systems. So we do need to increase the number of qubits, which would be this direction, but actually more importantly, we need to decrease that error rate. So I said these things are very fragile down there. They last right now about 100 microseconds in our systems. Which is a very short period of time. Actually, but it's a really good period of time for qubits. We're pretty proud of the number right now, but it's actually still very short. So you can see, if I had a 50 qubit system that had the error rates we have today, and I moved to a 100 qubit system, my quantum volume would go up by 0. That is, having the extra qubits isn't helping me because I can't literally entangle all of them and actually manipulate them to get them to a very deep circuit or deep algorithm before they've all reset themselves to something that's the wrong answer. On the other hand, if I stayed at 50 qubits but actually decreased my error rate by about 10x, I'd actually have a 500x improvement in our quantum volume in terms of the kinds of algorithms I could actually run on it. So the whole future of the industry is to go kind of diagonal, right? Continue to decrease the error rate while we build more qubits. And the building qubits is actually not the hard part. It's definitely the error rate that's the hard part right now. So what kind of problems can you solve with it? So obviously there's a set of problems we're going to call easy problems, and I'm not trying to be in any way judgmental, but they're problems we can solve on classical systems, so we'll call those easy. There are another set of problems that are called hard problems. You probably heard like NP hard problems, things that we can prove grow exponentially when you try and get to a larger and larger problem set. And many of those cannot ever be solved on a classical system. The traveling salesman problem is a very famous version of that, right? Of those hard classical problems, there is a subset that is quantum possible. That is, we believe you could solve them on a quantum system. And that's why it becomes really interesting. But to be really clear, it's a subset. So for example, the completely unrestricted traveling salesman problem cannot be solved on a quantum computer to the best of our knowledge or understanding of how that problem would work. However, there are very important versions of the traveling salesman problem that could be solved on a quantum system with at least quadratic, if not exponential, speedups compared to what you can do on a classical system. So that's why people are really interested in quantum for optimization problems, for example. Machine learning, well, chemistry and materials already mentioned are ones that I think are pretty straightforward. You're emulating quantum systems with quantum systems, so I think that's pretty straightforward. And machine learning as well. There are some problems in machine learning we think could be applicable to quantum systems, and we'll talk about those. The one I didn't actually mention yet is factoring, which is using these to factor very, very large numbers, very, very large numbers in their prime factors. But it's the one most people think of first for quantum computing because there's this fear that we're going to break the internet because a quantum system can factor very large numbers. All of our internet encryption right now is based on not being able to factor very large numbers efficiently. So in one sense, they're right. It is true that if you had a large enough quantum system, you could absolutely factor very large prime numbers into prime factors, and you would break the versions of encryption we use today on the internet. To do that, though, you'd have to have a system that was at least thousands, if not millions of qubits, and they would have to have error rates that were 2 to 3 orders of magnitude better than what we can do today. So our best extrapolation is you're not going to see anything like that until at least 10 to 15 years from now, at best. In fact, there's some speculation as to whether it's even possible to build a system that large and really be able to do that depth of circuit, given just the physical realities of trying to deal with qubits. That being said, assuming you do want to be ready for it, there are already ways today you can do classical encryption that does not map onto a quantum system. A lattice cryptography, for anybody who's familiar with it, is a form of cryptography that we can do today. It's a classical problem that fits more in the hard problems for classical computer, hard problems outside the quantum side. So we could use that today, encrypt things, and then when quantum systems come up, no matter how big they get, they'd be no better at breaking that problem than the classical system is, because it just doesn't map onto what we can do with quantum systems very efficiently. So when we talk to our clients, because obviously we deal with mostly big companies, we say, it's way too early to worry about anything you're doing on the internet. You've got a long time before you have to worry about it. But if you're talking about encrypting your data, and you have data, say medical data, financial data, government data, that you really would like to keep secret for more than 10 to 15 years, it's not too early to think about how you encrypt that. Right? Because you aren't going to go 15 years from now and re-encrypt your entire tape archive, with some new encryption technology when quantum systems come out. So it's not too early already to start doing that, so that you are kind of quantum proofing yourself, I guess I'd say, along the way. So we have started to do stuff even with these small systems we have today. As you'll see later on, there's an IBM Q system that's available on the cloud today that anyone can go use for free. I encourage everybody who hasn't ever gone there, just Google IBM Q and you'll find it. It's got both a 5-qubit system and a 16-qubit system that you can use today. You can run a simulator as well as doing it in real life. And we've already published some papers on it. IBM in 2017 published a simulation of a very simple molecule, lithium hydride, so just 2 atoms. And you can see the pink line is the exact answer. And of course, we know it because it's just a small atom molecule. You can easily do that on a normal computer. And you can see that the quantum system got it okay, but it's actually not exactly on it. And it's not because we had 7 qubits, which was actually plenty for doing this problem, but they have a lot of errors still, and they're very noisy. So you can see we didn't quite get it right. About a year later, we actually published again, and now we were actually right on. So we were about 10x better. Partially, the error rates got better, but very little. Actually, what we'd figured out was how you could actually controllably inject more noise into the system. And then we watched how those points changed, and it turns out they changed very deterministically based on having more noise. So we kind of got it worse and worse and worse, and then extrapolated the other direction to say, well, if I went to 0 noise, what would they look like? And lo and behold, the algorithms came out, and you actually can get it to actually match. And do it repeatedly, not just like by knowing where the pink line is. You're actually doing it and then seeing if you got the right answer on it. And the reason I bring this up is we're in this phase right now that we like to call noisy intermediate scale quantum computing, or NISQ, N-I-S-Q. Where these systems are not going to behave the way we'd like a real robust system to behave. But by playing with them, we really do believe we're going to find ways to actually get advantage of them long before we have a system that can just solve the whole caffeine problem, for example. And a lot of that, by the way, is going to be by combining what we do on the quantum computer with what we do on standard HPC systems. I have a group at Allman who does HPC simulations for chemistry in general, and they're now spending a lot of their time figuring out what are the really tough problems for the HPC system that I can do on the quantum system at a scale that is reasonable, that would then allow me to feed the HPC system in a way that would let me eliminate a whole bunch of stuff I would have to look at otherwise. So I think there's a lot of work to be done there. We also published a paper on how to use this for machine learning. A common problem in machine learning is to classify data that's in some dimension. So if you've got the data there on the left, light blue and dark blue dots, and they're in a linear line, and I say, draw a line to actually separate the light blue and the dark blue, you can't draw one line, right? There's no one line that will separate those data. On the other hand, if I raise the dimensionality of this, so I actually take it up to a higher dimension, in this case, very simply, I squared it, so that's just 2D, you can now easily find a line that actually separates the data, the light blue and the dark blue data. And there's a whole set of machine learning problems that we do on this, that's actually what we're doing. We're raising the data that we have up into very high dimensional spaces and trying to find a hyperplane that actually now divides cats and dogs, or whatever it is you're trying to classify, right? And we do this with neural nets and all sorts of other ways, but you could actually do it in a quantum system as well. So we published a paper. We had a very complex set of golden and black dots there, and it was able to find a very bizarre looking algorithm that actually separates them out in the equivalent of a hyperplane in one dimension in the hyperdimensional space that it put it on. The important point here wasn't that it was that interesting. It was we used this to prove the importance or try and show the importance of entanglement. The fact that if we just use superposition on these and tried to use it that way, it turns out our answers were not actually all that good. When we started to entangle the qubits, so then we were able to actually have them rely on each other and how they were actually zeroing in on the right answer, we found we get better and better answers along the way. And this is important because we're still at the stage in quantum computing where people don't actually know what is going to be important, right? What's going to be the real key factors? I think you guys had somebody here a couple weeks back from D-Wave technology talking about the D-Wave systems they've got, which are a very different structure. They actually are, I think they have like 2,000 qubits now at this point, and they're all kind of spread out in an array for doing what they call quantum annealing style problems. And quantum annealing problems do not rely on entanglement, but they do rely on setting them up in the various superpositions and then allowing them to relax down to low energy state. And in theory, there are problems that can solve that would have advantage over what you can do in a classical system. I would say there's a raging debate in the academic community as to how much advantage and whether it really gives you everything you want, but clearly there's a lot of people going on and doing research there. We've obviously gone a different way. We believe that entanglement is going to be really critical, and having this kind of gate technology that you can program is going to be really the way to go forward on it. But actually, we keep watching D-Wave very carefully because that's actually a very interesting approach as well. All right, so in terms of time frames, quantum chemistry, things like that, maybe less than 5 years. You have to be in probably the 100 to 1,000 qubit range before you're going to do something that's actually of interest, I mean, that the business would care about. If you want to do Shor's algorithm or big linear algebra problems, Shor's algorithm, by the way, is the factorization algorithm, the one that could break the internet. You've got to be, as you can see, 10 to the 8th or so qubits, 10 to 15 years if it's even possible to get to that level. So we do believe in the near future there's going to be things that really are interesting, but we got a long way before we get to the sort of nirvana of being able to have a giant quantum system. As I said, we do have the IBM Q experience out there. We released it in 2016. It's very user-friendly. It's got a graphical interface that you can go and literally lay gates down to actually program the qubits. There's also, though, increasingly Python scripts. There's a bunch of Jupyter notebooks out there. People are putting up programs all the time. It's all open source and everything. There's a programming language we call Qiskit that actually we released a couple years ago and we continue to support, which is basically a programming language. Quantum Information Software Kit is what it stands for. To be able to allow people to actually do programming on these systems. We are trying also as part of that to make it easier and easier. This is just a visualization of all the people running the systems from all over the world on a given day. It was May 11th, 2018. And we've had over 100,000 users, which, by the way, shocked us. When we put this thing out there, we figured, a few hundred people know enough about quantum computing to even bother looking at this thing. But from the beginning, we had huge numbers of people using it from all over the world. All 7 continents you see, there is in fact a scientist who's down in Antarctica who's got a lot of time in her hands and she's taught herself quantum computing and she's been using it from down there to actually run things, so it's kind of cool. Anyway, a lot of people going after it right now. As I mentioned, this Qiskit, which you'll find on the website as well, it's got a lot of things to program at all sorts of levels, so no matter where you are in understanding quantum computing, you can actually go and play with it. We're increasingly trying to do a set of libraries, like if you're a chemistry person and you understand algorithms for chemistry, can we get a few of those simple ones and then map them onto the quantum system so you wouldn't have to understand how that part works? You could just use the algorithm you're used to using. So we want to get more and more of that kind of stuff happening. And we encourage, by the way, people in the community to put stuff up too. I mean, this is all open. This is not for IBM's proprietary use, because that's the way we think we'll really grow an ecosystem around this kind of capability. Lots of different universities and companies and such involved. I point out we even have some fairly major banks involved. JP Chase was on a panel last summer. They have 10 people working full-time right now on quantum, even though they fully acknowledge it's going to be 5 to 10 years before they think they'll get any real benefit out of it. But if they're able to actually shave a half cent off a bond price before their competitors, that's real money. So they're willing to kind of play the bets now on this. Okay, so wrapping up, I've talked about the different forms of computing we're going after. Obviously, it's going to be a very hybrid cloud world in the future, and this is not just some in the cloud, some on-prem, but you're going to have your quantum computer probably on someone else's cloud. You might have AI accelerators somewhere else. Really think about how we actually manage all that is one of the biggest challenges we see right now. Part of the reason IBM bought Red Hat, if those of you who know, last November, was because we believe this idea of managing all of the clouds, no matter whether you want to run Amazon or Google or Microsoft or us, we want to be able to manage it for the enterprise in an efficient way. Beyond that, we also think that there's have to be a lot more automation for the programming that goes on. The amount of effort that it takes right now to do programming, particularly for these deep learning networks and things, is escalating faster than what we actually have people to go do it. So it's a challenge if we don't figure out more ways of automating that. And then lastly, we want to think about what kinds of applications we could actually use, we could really take advantage of all of these different forms of computing. And I'll just leave you with the one that we're focused on right now, which is materials discovery. So how do we go about materials discovery today, or chemical discovery, or drug discovery? It's largely very empirical, very Edisonian. You just keep mixing things and trying them, and mixing things and trying them. And yeah, we do simulations on HPC systems as well, but like most simulations, they're good after the fact to tell you why it worked, rather than telling you what you should have gone and done in the first place. But we think if you combine this stuff together, obviously you'll keep using HPC for some of the simulations. You got a quantum system that could do much more exact simulations. Not of the ground state, but that's kind of just an interesting sidelight. But could you figure out ways to figure out the exact energy states as molecules reconfigure themselves in key reactions to find new catalysts, or find ways that how's this protein really going to attack the cell? Where's it going to actually attack on the cell? These sorts of simulations, potentially quantum could help out with a lot. And then even on the AI side, AI for two things. One is the number of papers that get produced in any field of study, but materials and chemistry in particular. 50,000, 100,000 a year. None of us read all of them. And I don't know who reads all of them actually. But if you could have a system that could read all of those and actually highlight, hey, this paper came out from this other area of research, but happens to be using the same material that you're working on, and actually highlight that to you, so you could actually go look at it. That could be a huge productivity gain, right? But it's got to be really understanding the paper. It can't just be, you can do that today on keyword searches on Google Scholar, right, to go find every paper that's on some random material, but you still can't, you'll get too many hits, you'll not be able to do anything with it. But if it actually understands what you're going after, understands a little bit more about how you read the paper, then maybe you can actually have something that help you surface the more relevant papers more quickly. And also, even when you're looking at the space that you're looking at for, say, different chemicals or molecules you're going after, huge amount of space of different combinations of atoms you could be doing. Could AI help us zero in on areas that might have be most productive based on what it learns of patterns on how molecules are interacting with each other? Of course, all those, again, will be managed by the automation and the hybrid cloud. But in the end, I think that's really where we see computing ending up. A much more complex world, much more a combination of CPUs for still the mainstream, all the control, all of the main processing still goes on there, but accelerators now, they're in a sense on steroids, right? So you have AI accelerators, you have quantum computing as an accelerator as well, and managing that all together. So a much more complicated world. I would say I'm a hardware guy. My background is semiconductor devices and physics, so I'm excited because it's getting interesting in the hardware world again. After 50 years of just scaling and getting smaller, there's some really interesting stuff to do. But I will say it's going to put a lot more burden on the system side and the software side to really take advantage of it in the future. So with that, I'm happy to take some questions.